Hello, in this video we'll be discussing the concept of electromagnetic radiation as it pertains to chemistry. So what we really mean when we're talking about electromagnetic radiation, as far as chemistry goes, we're going to focus really on light. And so light, I've sort of drawn out the diagram of the various sections of waves associated with it. And you go from all the way from gamma rays down to radio waves. And they're on a spectrum determined by frequency up here, so this symbol up here means frequency, and wavelength, which is represented by this symbol down here. So as you go this way on the spectrum, you are increasing your wavelength. And as you go this way, you're increasing your frequency. So wavelength and frequency are inversely related to one another. As you increase one, you decrease the other. So as you go down the spectrum, as you increase in your wavelength, you go from gamma rays here to X-rays to UV rays, which stands for ultraviolet rays. You have the visible spectrum, and this is the chunk of light that we can actually see with the human eye. And it's interesting because it's actually a very small sliver of the possible spectrums of light that we can't see. Then we have IR rays, which are infrared rays, microwaves, and then radio waves. And in chemistry, generally we're going to focus on X-rays through microwaves. So when you get down to it, light can be represented in two different ways. You can either have a light wave or the light particle, which is known as the photon, represented here. And what's interesting is that light exists as both of these things simultaneously. So light has a property which is called wave-particle duality. And that just simply means that it can exist as both a wave and a particle. And it's interesting because electrons also share this property. Electrons also exist as both waves and particles. And the photon in particular is known as a particle of energy. So we owe a lot of what we know about light and the functions of light in chemistry thanks to a very famous atomic physicist named Max Planck. And what Max Planck discovered is that a particle of light, the photon, can be represented as a unit of energy called the quantum of energy. So he discovered that there's energy associated with a particle of light. And that energy, which is what we'll look at in just a second, can be passed off onto atoms and their electrons. But first, let's talk a little bit about light itself. So light has two key properties that you'll have to use in various equations in chemistry. So the first property is something we already talked about, wavelength. And wavelength simply means the distance between two peaks in a wave. So we have a peak here, we have a peak here, and the distance between them is the wavelength. So wavelength is represented by the Greek letter lambda, which looks like this symbol here. It looks like an upside down Y, and it's called lambda. And the units associated with wavelength are typically going to be meters. So you'll often see wavelength represented as meters. And the other key property is going to be frequency, which we also talked about. And frequency just means the number of peaks hitting at a certain point in a certain duration of time. And frequency is going to be represented by the Greek letter nu, which looks kind of like a V. So this V shape is called a nu. And the units associated with frequency are going to be reciprocal seconds. Now you can also see frequency represented in hertz, and they mean the same thing. So a hertz is the same thing as a reciprocal second, which is this s to the negative 1. And reciprocal seconds can also be represented as 1 over s, because that's what this s to the negative 1 means. It just means 1 over s, reciprocal seconds. So on to photons. So as I said, a photon can be considered a little particle of energy. And what Max Planck did is that he derived this equation to describe the energy of a photon. And he discovered that the energy of a photon can be summed up as this number here, which is called the Planck constant, multiplied by the frequency of the wave. And that will give you the energy of that photon in joules. So this can also be represented as another way, because we can write frequency as the speed of light over the wavelength. Just like that. So frequency is equal to the speed of light c over the wavelength lambda. And that way we can substitute, and this is often how you'll see it, you'll often see frequency substituted with speed of light over wavelength. So you're very likely to run into this equation for the energy of a photon written in both of these ways, both as h nu and hc over lambda. You'll see it written both ways. So just to define the Planck number and the speed of light, so h is defined as a very specific number. So the Planck constant is equal to 6.626 times 10 to the negative 34th joule times second. And joules is the unit that's associated with the energy of the photon. So when you solve for the energy of a photon, you'll want to express that as in joules. And c, which is the speed of light, is equal to 3 times 10 to the 8th meters per second. So that's what you would plug in for c. And what we'll see in the future is that we can associate the energy of a photon as it interacts with atoms. So a photon can interact with an atom, and we'll see that when we look at atomic spectroscopy. And in a later video we'll also do some practice problems involving wavelength and the energy of photons. But this is just a little overview of light, and in the next video we'll discuss atomic spectroscopy.